As Heather introduced me, I'm Momo Ellwarth. I am a PhD student at Ansgar Reiner's group in Göttingen, and I would like to tell you something about the spatially resolved solar data we obtained at our institute quite recently. Okay. The most significant obstacle to achieving EPRV capabilities is the intrinsic variability of planet host stars. So this is one of the main findings of the EPRV final report of 2021. And as we know, to disentangle planetary signals from stellar signals, we need to understand activities and variabilities in a great detail. So if we want to reach extreme precision, we need to be able to mitigate stellar variabilities. And I think we heard a lot of that so far. Yeah, and there's not only the general variability of a star to be taken into account. We also have an effect of if we're resolving if we're resolving a star, for example, the sun, then we can see that the spectra, they change. If we're looking at the center of the star, we will obtain a different spectra. And if we're looking at the limb, yeah, they don't look the same. So we have a shift in wavelengths and also the intensity changes. And this is due to the fact that we have rotation here and also center to limb variabilities because of, if you're looking at the disk center, you're looking at different atmospheric heights than at the edge. Okay, and yeah, since the sun is close enough, it's perfect object for this kind of benchmarked observation, and that's what we have done and we're still doing at our institute in Göttingen. There you can see a picture of our institute with the solar telescope on the rooftop, and next to it a sketch with, yeah, a sketch of the sun, and every one of these tiny small dots are regions we have obtained observations. And our observations were done with a Fourier transform spectrograph. And yeah, the wavelength range we have is between 4,200 and 8,000 angstrom with a resolution of 700,000. And the signal to noise is between 400 and 700. And this is also depending because if you're looking at the disk center, you have a different signal to noise ratio than at the edge of the limb. Okay, and yeah, we have an absolute velocity offset so far from 30 to 50 meters per second with our data. And this is also depending on the observing angle. Then we added all of the spectra together for these different radii, the observation angles, to obtain in the end our center to limb atlas. I will show you one line here. There we can see on the upper panel is, it's an iron line at 615 nanometer, 617, sorry. And you can see here the EHT data on top, and we also compared it to Lars data, which is also center to limb. And the behavior is, it looks the same. We have a deep line for the disk center in blue. And then if we're going towards the limb of the sun, the lines get shallower and also more redshifted. And then you also see some bisectors of our resolved observations. And yeah, you can also, if you compare this, both observations, they match quite well with each other. And you can find those plots and also a bit of a general introduction of our data at the current paper, which is on archive right now. And yeah, then we also have another recent paper, which is also on archive. And there we compared 4 different lines who are often used for exoplanet transmission analysis, and we compared them to simulations. And here you can see 2 of them, the sodium and magnesium line, and our data is the the solid lines. And you can see in the first column, there we compared it with spectroscopy made easy, SME, LTE data. The second one in the middle is SME, non-LTE, and the third one, these are cobalt simulations, which are also LTE, but 3D magnetohydrodynamic models. And as you already hear, as you can see, that the models are often not quite well matching with the observations. And the second smaller plots below the lines, they also show the ratio between models and observations. So in general, we can say that we have large systematics here, and the models tend to overestimate also the center to limb variation. Because of this overestimation, we see this. So we use those lines and simulations in our data to simulate a transit. So these are the transmission curves here. And you see, because of the center to limb variation, because it's much stronger in the simulated data, you have a much bigger effect here. You have the transmission curve on top, and then also the ratio again below. And if we go further and use this simulated transit to plot some Rosetta-McLaughlin curves, then we can see that the difference between observations and the signals from the simulations, they show here a difference in the curves, so that we have a mismatch between the two sets, and this is in the order of 5 to 10 meters per second between the amplitudes. And this is quite a large effect we can see, just because we didn't implement the right center to limb variation to those lines. And I told you some stuff about single lines now, and then I also wanted to show you something which includes more of our spectral range. In 2016, Ansgar published a paper about the EHG solar flux atlas. This time it was for the integrated sun, and this plot shows just the behavior between the normalized line depth and the absolute convective blue shift. Khalid also showed it earlier. As we know, the deeper the line, the less convective blue shift. And now with our new data set, we also have the opportunity to have this information for the resolved sun. You can see here that the purple dots, they are for the disk center observations. And I hope you can see it here, but basically they match quite well with the integrated outcomes. And then you see this, this trend that the further you go to the limb of the sun, the less convective blue shift you are observing. And that's basically also what we saw before in the bisectors. And after that, it would be nice to have this information not only for convective blue shift against the line depth, but also for the formation heights. And we started this by, I have this plot where we plotted the convective blue shift against the mean formation temperature. So this temperature, we used the SME code for that. And you can see that the blue shift compared to the temperature also shows a pattern for different angles on the sun where you observe it. That's the last plot I wanted to show you. I'm a bit faster than expected. We'll end with my conclusion. The basic stuff I wanted to tell you is that our data set is quite helpful to study convection and magnetism of RV jitter, and also to understand transit observations better and improve models and so on. And also that you can download the data and just use it and work with it over this link. And the other thing for us, our next step is to improve our calibration within variability. We're already on that. And yeah, to reach a 10 centimeter per second precision. Yeah, and another next thing we want to do is to not only observe quiet sun, because now we just observed quiet regions of the sun. The data was from the beginning of our current solar cycle, so it was really quiet. And yeah, the next step is now to also get some magnetic regions to see the spatially resolved, to see them spatially resolved. Yeah, we have two posters. One is more technical and the other one more general over the science topic. So if you are interested, take a look, and thank you.
All right, do we have any questions for Momo? Oh, there's one over here. Mike is coming.
Thanks for a great talk. I was wondering if you could comment a little bit on what the implications might be for observations of exoplanet atmospheres with transit spectroscopy if we're getting
Can you speak a bit louder? Sorry.
Oh, sorry. I was hoping you could say a bit about what possible implications the work on revising center to limb variation models might have on our observations of exoplanet atmospheres with transit spectroscopy.
I think that, I mean, usually you use models to get your data, your signal, and if you use it like wrongly because you don't know what to subtract from your data, then you can have like shifts or transmissions who are like not there. I'm not sure if I can, but I think you would get wrong answers if you're not knowing the correct center to limb variation here.
Okay, so we're going to get the next speaker set up, and while we do that, we can have one last question.
Thank you very much for the talk. And my question is about your comparison with line depths. You have plot, and what I notice, you have kind of outliers from your general distribution of mean formation temperature and absolute convective blue shift. My question, if you look why you have
this one?
This one, yeah, and you see you have many kind of points separated from general trend.
Yeah, I know. I didn't take a look so far into that because that was like the last thing we've done. So we need to find out, but maybe blends or because I didn't. That's all I can say.
All right, thanks. Can we thank Momo one more time, please?